Hello everyone. Welcome to this week's ECEGSA academic seminar. Today we are very honored to invite Chuan Shi and to give us a talk on Interleaved SEPIC PFC using component inductors for plug-in electronic vehicles. Chuan got his Bachelor of Science degree in electrical engineering from Wuhan University in 2013. He's currently working toward the Ph.D. degree at the University of Maryland College Park. He was an intern with Altera, Inc., Texas, USA during summer 2015. He was the recipient of 2016 Harry K. Wells Energy Research Fellowship from the University of Maryland Energy Research Center. His current research interests include modeling, analysis, design, and control of power electronic converters for plug-in hybrid electric vehicles, as well as other power management for battery, ultracapacitor hybrid energy sources systems. Now let's welcome Chuan to give us this talk.
Okay, everyone. So I'm from the Maryland College Electrical Labs, and today my topic is about the Interleaved SEPIC PFC. So PFC is a power fed correction converters. And I will use the carbon inductors, and these converters used for the electric vehicles. And so I spent like half a year on this project, and I just finished that. And I just published a paper on transaction electric vehicle conduction based on this topic. And so today I talk about this thing. So we know that the electric vehicle is very popular nowadays, and the Tesla has released many models on electric vehicles. And so for electric vehicles, we come to a problem that how we charge them. So there are many solutions about the charger. So now we can put the charger on board, or we can also use a power station to charge the electric vehicles. So there's two kinds of choice we choose to charge the electric vehicles. And so for the onboard battery chargers, that's for most of the time that's for low power. So the highest power now is 6.6 kilowatts. And if we use a power station, and for Tesla has a power station, supercharged power station, so that's for electric vehicles. So if we use a power station, we can charge the electric vehicles just in 30 minutes. So that's really fast. And for my research is about onboard charger, it's about the low power battery charger onboard. And so first let's have a look at the structure of the electric vehicle. So here, this is a picture about electric vehicles. We can see that we need to gather power from the grid. And the power grids, the different places have different power grids, so we need to consider that. So the voltage from the power grid range from 85 volts to 265 volts. So when we design the battery charger, we need to consider the universal input voltage.
Is that the peak value or the
RMS value? And so you can see that this battery here. So we put the battery on the car. So the battery will take the most of the cost in electric vehicles. So now we need to charge the battery. But for battery, we can only use the DC power. So that means we need to convert the AC power to DC power. So that's what the battery charger do. So just convert the power from the grid, the AC power to DC power, and use that DC power to charge the battery. And then the rated power, most of the time the rated power for the battery is 400 watts. And then we need to change the DC power to AC power and use this AC power to drive the motors in electric vehicles. And because most of the time we use the AC motors, not DC motors in electric vehicles. Because I mean AC motors for most time is better for maintenance. The maintenance is much easier for AC motors. And I think I know that Tesla Roadster, and they use the induction motor. So induction motor is a three-phase AC motors. So we need to convert this DC power then to AC power. But now today we talk about the charger part. And okay. So for the charger, we have some design requirements. So first, we need to put that on board. So that's on board. So location should be on board. And the second design requirement is that the electric isolation, because that's for safety consideration. So when we charge the electric vehicles, we don't want the battery direct connected with the grid. So we want to put an isolation between the grid and the battery. So we should consider, so we should design the battery charger as an isolated charger. So that's for safety reason. And so how we implement that? So we can put high frequency transformers inside the DC converter zeros. So in this way, the battery can be isolated from the grid. And normally, so you can see there's a two-stage here. So nowadays we use two-stage battery chargers. So you can see there's a PFC stage, this stage. So this will convert power from AC to DC, and there's a DC link here. So this is rated at 400 watts, and then we use a DC converter to implement the isolation. So here we need two different kinds of stage. And for this DC-DC converters, so we use the LLC. Most of the time we use the LLC DC converter. So that's a resonant converter. So the resonant converter, so that's some concept from the power electronics. So resonant, we use a resonant phenomenon to convert energy from DC to DC. And because that's a resonant, so we know that, so it's AC. So we need to use a high frequency transformer inside this converter to change the power first from DC, then to AC, and AC to DC. Okay, so that's just for isolation. And the resonant converter, so we can have many advantages, and there are at least 3 of them. And they can implement soft switching, and that's for improve the efficiency. And because here, so all of these converters is composed of the inductor, capacitor, and the switch and diode. So we operate the switch, the switch in high frequency. So we need the soft switching to ensure that the power loss in the switching is very small. So in this way, the efficiency can be very high in this case.
Okay, question. So what is the typical voltage on both sides of that DC-DC converter? Is it down converting or up converting?
So this DC converter, yes, that's a good question. That's decided by the control strategy we use. So we can control that DC converters as a unit gain. So the gain unit is 1, and so we can control this DC link voltage. But we can also fix this DC link voltage and control this converter to step up and down the voltage. So that's decided by the control strategy we use. And okay, so we also need to. Okay, that's for DC converters. But from today, what I talk about is the AC-DC converter, because that part is fixed. That part is fixed. AC converter, resonant converter, and the resonant converter is very good and operated in high efficiency. And today I talk about the AC-DC, this PFC part. So my topic is about the PFC converters. So that's a PFC converter. I will focus on that. And okay. For the PFC converters, there are two candidates. The 2 options. One is boost type. So boost type is the topology like that one. So for the specification for that is, the output voltage has to be higher than the input voltage. Always like that. The output voltage cannot be lower than the input voltage for the boost type. AC-DC converters, the PFC converter. So that topology can only use for step-up. But here, there's another topology, the SEPIC type PFC converters. And this topology can both step up and step down. So that means output voltage can be lower than the input voltage if we use that topology. So here we come with this problem. So which topology should we choose for the first stage, AC-DC converter? And so that's decided by the DC link voltage, right? So we want the DC link voltage to be fixed, or we want the DC link voltage to be variable. And so I can tell you that the traditional strategy is to fix the DC link voltage, and the traditional topology is the boost type topology. So in that case, the output voltage has to be always higher than the input voltage. So that means the DC voltage is always set at 400 watts and to be a lot higher than input voltage, and they're always fixed there. So in that case, the traditional, this is a schematic to show the traditional control strategy. And you can see that so we use the boost topology here, boost type converter here. So we first step up the voltage, and that's DC link voltage, the higher than input voltage, and then we use the DC converter to change the output voltage. But this will come another problem. So the DC converter, resonant converter here we use, is not suitable for this kind of control. So when the output voltage is much lower than input voltage, so the efficiency of the DC converter here we use, will be very low. Because remember, I just talked about the soft switching. So when output voltage is much lower than the input voltage, the DC converter cannot implement the soft switching. So in that case, the efficiency will be reduced a lot. And okay, so that's the problem with traditional control strategy. And so you can see that the disadvantage is, the output voltage is lower than input voltage, and we cannot use the unit gain. Because for the DC converter, it's better to control that at unit gain. So in this way, you can maximize the efficiency, and you can control at the resonant frequency. That's something about the resonant converter. And okay. So this is the proposed control strategy. So you can see that the DC link voltage is not fixed there. So we use the AC-DC converter to control the DC voltage. Because previously the boost topology can only implement the step-up control. But for this static topology we proposed can control the DC link voltage to be lower than the input voltage. So in this way, we can implement the unit gain of this resonant converter. So in this way, we can improve the efficiency of this one when the output voltage is much lower than the input voltage. Okay. So that's the reason why we propose this SEPIC PFC converter. Okay, so the solution is SEPIC type PFC converter. But for the SEPIC converters, we also have some other topologies. So we also need to consider which topology we choose for the SEPIC converter. So the traditional SEPIC converter is like that one, and this is the proposed SEPIC converters. And this converter is interleaved, so we can see that the only difference is we have two phases here. So traditional one just have one phase, but for the proposed SEPIC, we have two phases. You can see there's a two phase, and when we control that, these two phases are 180-degree phase shift. So in this case, we can reduce the input current ripple, because this is connected with the grid. So for the grid, we require that the power from the grid cannot be distorted. So in this case, we use the interleaved topologies. The input current will not be discrete much, so the total harmonic distortion will be much less than the THD value. So did anybody know THD value? Okay, so the THD for this SEPIC PFC will be much lower than the conventional SEPIC. Another thing that because we use two lag here, so the power level for the proposed SEPIC can be much higher than the traditional one, right? Because we use two lag, two phase of SEPIC converter.
So what is SEPIC? What is the full name for SEPIC?
SEPIC converter is the name of that one. So that's a single and the primary inductor converter. So if you're interested in that, you can Google it. Okay. And the name is very long. Okay. So that's SEPIC PFC converter. Okay. Another thing that you can see that because we have two lag here, so we have four inductor, but for this proposed topologies, we couple these two inductor. So in fact, when we implement this four inductor, we just have two magnetic components. So we just need two cores for this one. And the number of coils is the same as the traditional topology. Okay, so we have just had a look of the proposed topology. So here we come up to a question. So why we interleave them? Why we use coupled inductors? Because if we interleave them and if we couple the inductors, the cost of the AC-DC converter will increase. So why we do that? Because we have many advantages over the traditional topology. Okay, so why we interleave them? So we can see that for the SEPIC converter, the voltage stress on the diode, that is the D1 there, and the current stress on on the switch. So voltage stress and current stress means the maximum voltage over the diode and the maximum current flows through the switch. So for the SEPIC topology we choose there, the voltage stress is very high for the diode, and the current stress is on the switch is very high. So if the current and voltage is very high for the power switch we use, that means the power rating cannot be very high. So that means this topology is only suitable for the low voltage case. So that's the reason why we interleave them. So with two lag. So in this case, the voltage level can be higher than the traditional one. And for the battery charger, the power rating most of the time is 3.3 kilowatts and 6.6 kilowatts. So the traditional topology is not suitable for that power rating. So that's the reason why we interleave them. Okay, so here there's a table show the voltage stress. For the traditional one, I mean that's the input voltage plus the output voltage. So that's the voltage stress, and the current is input current plus the voltage current, output current. Okay, so this gives us the reason why we should interleave it. Okay, so higher power rating, and the traditional SEPIC topology is not suitable for the high power application. And you can see that the input power current repo is less, and the output voltage repo is also less. Okay, so second question is why we interleave the inductors. So because we have two phase of SEPIC converter, so we use two SEPIC converters here. So we have 4 inductors and 2 capacitors here. So if we use 4 inductors, I mean the size will be very large. So when we design a converter, we cannot make the size very large because that will take a lot of space, and also the cost will be much higher. So in this case, we couple it to reduce the size and reduce the cost. So this is a cover inductor. So this is what I made in the lab. So you can see that this is one coil here, another coil here, and just equal to connect these 2 coils. So these 2 coils are coupled with each other. So when we use cover inductors, we can see that we just have 2. In fact, we just have 2 equals it. One here, one here. So the size can be reduced a lot. And also, if we couple 2 inductors, so that facilitate the DCM operation. And so, okay, so later, so for the DCM operation, so I will show some pictures on that. Okay, so this is a comparison between the proposed SEPIC and the traditional SEPIC. So the number of magnetic components is the same as the traditional one, but the power rating is much higher and the efficiency is much higher than before. Okay, so we just talked about the coupled inductor. So now, we need to figure out what the coupling coefficient should be look like. I mean, should we design for the coupling inductor? So we should weak couple this. I mean, we should weak coupling the 2 inductor, or we should strong coupling the inductor. So that's a question we should figure out when we design the coupling inductor. And okay. So in order to address these problems, we have to propose this. I mean, we have to first give this equivalent circuit of the SEPIC converters. So the equivalent circuit for the capacitor here, previously there are 2 capacitors here. So the equivalent circuit for that is 2 voltage source. And the voltage source is the same as the input voltage. Because if you measure that, you can see that the voltage over the capacitors follow the input voltage. So we just equal the capacitor to a voltage source. And for the switch, we just equal it to the ideal switch. And for the cover inductors, so the equivalent circuit is 3 inductors here. So this is magnetizing inductance, and these 2 are leakage inductance. If we do analyze for that, we can get an equation like this one. So D is the duty cycle. Duty cycle is a signal we send to the switch. So when we control the converter, we have to control the signal we send to the switch. And so that equation told us what the reference voltage should be like through time. And here is some waveform of the converter. So the first two waveform is a signal we send to the two switch, and this is the current of the couple inductor, and this is the current that goes through the diode. So for this waveform, based on this waveform, we can see that just there are different operation modes. So you can see that there are 6 of them total. It's 6 in total for the operation mode. And this is operation mode 1. And okay, I think this is 2 PHEVs. So okay, let's just look at this. So this is mode 2 and mode 3. Okay. And so this is a high output voltage case, and previously that's a lower output voltage case. So that means this case the output voltage is higher than the input voltage. So the waveform is a little bit different from the previous case, and we can calculate the current ripple here. The current ripple is subject to that equation, and you can see that we derive equation for the coupling coefficient. So K is coupling coefficient here. So that's related with the induct current. So by using that equation, we can figure out the coupling coefficient for that. So here I give a list. So that's the minimum coupling coefficient we should choose for the coupled inductors with respect to the inductance value. So you can see that when the inductance value increase, the coupling coefficient should also increase. And for this design, so I choose this value, 400 microhenries, because this value also designed by the input current ripples. So we should also limit that input current ripples. So we choose a 400 microhenry for the inductance and a 0.8391 for the coupling coefficient. So now we know all the factors for the coupling coefficient. So now, based on these two factors, we can implement the coupling coefficient, the coupling inductor. Okay, so this is the design specification for the SEPIC converter which has proposed. Okay, so this is simulation result, and you can see that it's very similar with the theoretic waveform. So this is the board I made, and for the SEPIC converters, you can see there are 2 coupled inductors here, one here, one here, and 2 capacitors here. So I use a film capacitor to fill these 2 because the AC current that goes through this film capacitor is very large, so we cannot use the aluminum capacitor. So we should use a film capacitor here. So the aluminum capacitor is just for DC link, and so we have a heatsink here, and heatsink is for switch and diode. So 2 switch here, 2 diode here, and that's the input port, and this output on this is for DC. This is for DC output. And okay, so this is some test results. So this test will take me a lot of time to test it, because sometimes I test a circuit and the switch goes and the switch burn, and you can smell something burn. And in order to get this test result, it takes me like 1 or 2 months to get it. I mean, this picture is the first time I made this board, and I take picture, and because it's burned many times, so it's not good at this anymore. Okay, this is the waveform show the functionality of this PFC converter, so input voltage, input current, and the output voltage. So you can see that input current is in phase with the input voltage. So that means we only get the active power from the grid, not the reactive power. And the output voltage, you can see some little bit of ripple. So that ripple is meet the requirement. I mean, so okay, so that's my design and my test results. Okay, thank you everyone.
So
You guys have any questions?
So the power is 370 watts, right?
Yeah.
And is that enough for an electric vehicle, or it's just like a prototype?
Just the prototype. Because I mean the size here, the size I designed here is not large enough. So if I want to increase the power, I need to use larger capacitance and larger inductors. So this is just for the visualization. This is just for the
Okay.
Yeah.
So it should be scalable, right? If you want to build some real, like, usable for a vehicle, like.
Yeah, right. So in real case, we should redesign these things and make the larger already.
Okay, let's. Any question? Let's send our speaker to this.